Lesson 9.1 on the Pythagorean theorem. Before we get to the actual theorem, we're going to go over a few vocabulary terms that are a part of the theorem. If we're working with a right triangle, the legs of a right triangle are the two sides that form the right angle in that right triangle. There in that illustration, the green-sided sides are the legs of a right triangle. You'll see that they actually, where they join, is where the right angle is formed. And the hypotenuse is the side of the right triangle that is opposite the right angle. There in purple in the diagram, that side length is the hypotenuse. Now the Pythagorean theorem, many of you are probably quite well versed with the Pythagorean equation, a squared plus b squared equals c squared. But the theorem actually says that the sum of the areas of the squares formed by the legs of a right triangle is equal to the area of the square formed by the hypotenuse. Now that is a lot of words to take in here, so let's break it down. First of all, we're working with a right triangle. So let's begin with the right triangle. Now, the theorem begins by saying the sum of the areas of the squares formed by the legs of the right triangle. So let's form some squares off the legs of each right triangle there. Now the sum of these areas. So if we were to calculate the area of each of these two squares and add those areas together, we would get a result that is equal to the area of the square formed by the hypotenuse. This is where we get Pythagorean's equation from, the a squared plus b squared equals c squared, where if we square each leg of a right triangle and add those results together, it will equal the square of the hypotenuse. Here's an example of the Pythagorean theorem in action. Let's find the length of the hypotenuse in this right triangle below. We know that both legs are 10 and 15 in length. So if we use Pythagorean's equation there and square 10 and square 15 and add that result together, it's going to equal the square of the hypotenuse. 10 squared is 100, 15 squared is 225. Add them together, we get 325. Now at this point, you're probably familiar with undoing squaring by square rooting. If we were to square root both sides of the equation, we would get c equals, but not exactly equals, is approximately equal to 18.03. I had to do some rounding there because the square root of 325 is an irrational number. The decimals don't stop. But we don't like rounding in math because rounding destroys value. Instead, let's find a way of taking that square root and simplifying it without destroying its value. Here's how we can do that. Simplifying radical notation, let's say that we have, again, c equals square root of 325, and we wanted to simplify the square root of 325 without destroying any value. There are two methods to do this. The mathematically preferred method in terms of understanding the properties behind it is the perfect squares method. We can take a square root and write it as a multiple of square roots. And our goal is to find multiples within the square root that are perfect squares. Perfect squares are, say, for example, 1, 4, 9, 16, 25, 36, and so on. Numbers that when you square, a number that is squared, for example, 2 squared equals 4, 6 squared equals 36. These are perfect squares. And if we can take the square root of 325 and split it into a product of two square roots where one of those two square roots is a perfect number, perfect square, say, for example, 25 is a perfect square. We can take square root of 25 times the square root of 13, extract the perfect square, and then simplify the square root of 25 to get 5. And so the square root of 325 simplifies to 5 times the square root of 13. But the problem with this method is that most students have a difficult time seeing factors that are perfect squares, let alone any factors that are greater than, say, 10. A more preferred approach by most students is the prime factoring method. Let's take 325 and prime factorize it. Now you can prime factor it using a factoring tree, or you can prime factor it using long division, a scale of long division. But let's start here. 325, the number ends in 5, so we can divide 5 into 325 and we get 65. That number also ends in 5, so we can also divide 5 into 65, which equals 13. Now, when doing the prime factoring method, after we have prime factorized our number, what we'll do next is we'll find any duplicate factors. These prime factors here are important. You'll notice there that there's a duplicate factor of 5. So what we're going to do in this procedure is we're going to rewrite the square root of 325 as the square root of 5 times 5 times 13. And whenever you have a duplicate prime factor, cross out that pair of prime factors and pull one of them outside the square root. And so the square root of 325 simplifies again to 5 times the square root of 13. Most students prefer this procedure over the perfect squares method, as it's much easier to factor tree or prime factorize a number than it is to try and find perfect square factors within a number. Another brief example, let's say that we had the square root of 320. So we can prime factorize the square root of 320, and if we do that with a factor tree or doing a long division method, we'll get the square root of 2 times 2 times 2 times 2 times 2 times 2 times 5. Let's take each duplicate pair of squares, perfect square factors. Here we have a pair of 2's, cross out the pair, bring one outside. Here we also have a duplicate pair of 2's, cross out the pair, bring one outside. And finally, one more duplicate pair of 2's, cross out the pair, pull one outside. We still have 5 left over as a unique factor that doesn't have a pair with it, so that stays under the square root. Multiply out our factors that we pulled outside the square root, 2 times 2 times 2, and we get 8 square root of 5. And that's how we can simplify the square root of 320. Thus concludes today's lesson.